All right. Let's wait a minute until people get back into the room.
We got 12 so far.
Yes. Great. Okay, well, welcome to the next session of the Scheme and Functional Programming Workshop. We had our first invited talk by Jeff Siskin, which was great. We got to hear about how Scheme can be used for deep learning. And one of the key techniques of that was automatic differentiation. And so for this talk, which ties into what Jeff was talking about, we're going to learn about adding automatic differentiation to Scheme by differentiating the interpreter, which is the sort of meta technique, which I always love, when you can do the thing by doing the thing to the interpreter for the language. And so you can see that Jeff is one of the authors along with Barak, and our lead author who's going to be giving the talk will be Mehrdad Maliki. So please take it, Mehrdad.
Thank you very much for the introduction. Adding an AD to scheme by a differential interpreter, which says it is a joint work with Barak and Jeff. Please let me start with the concept of differentiation. There are many different equivalent ways to define the derivative, but here we use a non-standard interpretation of computing derivative by use of dual numbers, and we use it as a way to adding AD to scheme. The classic definition of the differentiation of a function from Euclidean space to another Euclidean space is a linear map which approximates that function at a given point. So this definition may be not working for computing the derivative form, so we need some intuition from this definition to work with. The tangent space actually is a key part of defining the derivative of a function, and informally, a tangent space is generalizing the concept of tangent line of a function in a one-dimensional case. So a tangent space of a manifold M at a given point x, denoted by T of x of M, is a linear space, linear vector space that approximate that manifold at the nearby point of that point. For example, if here we have unit circle S1, and at point X we have a line which is a vector space, and the vector V belongs to this tangent space, and the union of all of this tangent space is a tangent bundle to this unit circle, and we call it by T of S1. You can see that subscript X omitted here because it is a disjoint union of our tangent space. And the element of tangent space are pairs, which the first element is the element of the manifold, and the second one is the element of the tangent space. So the second one belongs to some vector space, but the first one belongs to maybe nonlinear manifold. So if we want want to define a derivative of function, for example, from a sphere to a torus, uh, we need to define d of f on the tangent space of this sphere to the at the point x, to the tangent space to the torus at the point f of x, which function f maps point x from the sphere to point f of x on the torus. And we call d of f on subscript x on v at the push forward of v by f. So if f is a function from manifold n to manifold n, then t of f from tangent bundle n to tangent bundle n is a smooth function between tangent bundle, and we call push forward of f. In this figure, you can see the function f that maps a sphere to the torus, and the push forward maps a tangent space at point x to a tangent space at point f of x on the torus, and push forward for vector v on the tangent space is the vector d of f of x on v on the tangent space of f of x on the torus. But as you can see, real numbers are Euclidean space are also a smooth manifold, so we could apply tangent bundle on the real lines as a smooth manifold, and it is isomorphic to Cartesian product of R with R. The first R is a manifold, and the second R is a tangent space of this manifold, which is isomorphic to itself because it's a linear space. And if this class is be a usual addition of real numbers, then push forward of the sum is a function from tangent bundle of R times tangent bundle of R to tangent bundle of R, which if we apply this to pair x and x prime and y prime, it gives us x plus y, x prime and y prime plus y prime, which the first x plus y is the element of on the manifold, and the second x prime plus y prime is the real number on the tangent space. And also, the push forward of the multiplication defined naturally as follows. T of push forward of the multiplication on the pair x and x prime and y prime belongs to tangent bundle of R is multiplication of x and y and x prime y plus x times y prime. And again, the second part is belonging to the tangent space at point x times y. But this definition relates to the concept of dual numbers, and a dual number is of the form x plus x prime epsilon, where x and x prime are real numbers, and epsilon is a variable that epsilon to the power 2 is equal to 0. And we represent x plus epsilon x prime as a pair in memory x and x prime, like the complex number a plus bi, which we represent as a pair and a and b in the memory. So x plus x prime in this definition, x called primal and x prime the tangent part of the dual number, and we denote the set of dual number on real number R by d of R. And d of R is isomorphic to the quotient ring of polynomial over epsilon divided by the ideal epsilon 2, which actually is a power series epsilon truncated at epsilon 2. So you can verify this two simple property of addition and multiplication of dual numbers, like the addition and multiplication of complex numbers. And you can see the tangent part is like the element of the tangent space in the definition of the push forward. So we can see the duality between push forward of the addition and addition of the dual numbers. So the set of dual numbers we have seen that is isomorphic to the this ring R of epsilon over epsilon 2 and also is isomorphic to tangent bundle of R. And plus multiplication and sum in the set of dual numbers are simply a push forward of usual sum and multiplication in real numbers. And a derivative of a function f from Rn to Rn is a push forward function t of f from tangent bundle of Rn to tangent bundle of Rn. It means we lift the function to dual numbers to calculate the derivative. So, for example, if f be a function from real numbers to real numbers, then lift of f is a function defined on the set of dual numbers to dual numbers by the Taylor expansion of the function f on the dual number x plus x prime epsilon, which is f of x plus x prime f prime of x epsilon, and the terms with epsilon 2, what we truncate epsilon 2 coefficient, and we have this definition of lift function of function f. And if we extract tangent part of this lifted version of the function f with epsilon with x prime equal to 1, we extract derivative function f at point x. But lift of function f is actually push forward of f. Push forward of f is a function from t of r, tangent model of r, to tangent model of r, and it defines as follows: t of f on the pair x and x prime, which is a member of tangent model of r, is f of x and x prime times f prime of x, and the second part is the member of the tangent space of r at point f of x. And in this definition, f is supposed to be a primitive function. The good property of t is that a good thing about t is that t is compositional. It means t apply on the composition of f and g, f of g, f o g is a composition of t of n f with t of g, and is the super proof of this fact. But the general philosophy of forward AD is calculating the derivative by recursively calling function of dual numbers and extracting the tangent part that compute the derivative of the function. And that this accomplished by a non-standard interpretation which preserve the original prior computation, but add some extra information which capture the derivative as a tangent part of the function. So the general AD algorithm composes the function f to a simple function f1 to fn, and recursively call the transform function f1 to function t of f1, which is push forward f1, but it applies to this vector which contains two parts, primal and tangent part, and it can compute forward AD from inputs x0 to output xn. But however, if we see a function f as a function from manifold M to N, the derivative we have seen that is a linear function from tangent space of M at A to the tangent space of N at f of A. So the operator is a function from M to N to a we can say that dependent type A from M, and it actually take a function f from M to N. At the point A, it gives us a linear function from T of A of M to T of F of A of M, which T of F of M is a dependent type. So for a function from Rn to Rn, the operation works like this, and T of A of Rn to T of f of a of Rm, we could simplify this section by saying that because T of tangent space of Euclidean space are isomorphic to itself, so derivative operation is like function from Rn to Rm, which takes a function from Rn to Rm, and at a point in Rn, it gives us a function, linear function from Rn to Rn. And if we apply this definition for simple function, for example, linear function, it gives us derivative of linear function gives us linear function which are themselves. And for example, if S from R to R be usual sum function which is linear, then derivative of S at A1 and A2 is S, which means if we apply d of S A1 and A2 on X and Y, it gives us S on X and Y, which is sum of X and Y. And also, derivative of multiplication is like this. It gives us, at point A1 and A2 and X and Y, it gives us A2X plus A1Y. But another key idea in forward AD is that the closure conversion must commute with AD. It means this actually defines the semantic of AD for higher order function. So we can apply AD to any defined function, even a function. AD, we can make AD as a first class operator that operate as operator to code that use operator. And also we could do higher order derivative by nesting application of forward AD in the evaluator. But the way to achieve this goal is in interpreter is that value are in tractable form. So by manually perform AD on interpreter, we have two level, original level, level 0, and forward AD, which is level 1. At level 0, numbers are just real numbers, but at level 1, numbers are dual numbers. But by adding machinery to allowing level 0 to call level 1 from inside the target language, we could unify level 0 with level 1 by adding a level to the evaluator, to the interpreter. So we could generalize this to arbitrary level n, and but we need to add level to closure, and by lifting the closure by intermediate its level and lifting all values in its environment. For example, in level 2, numbers are double dual numbers, which prime and tangent parts are dual numbers. In level 1, the dual numbers, the primary part of the dual numbers are just real numbers, and the tangent part are also real numbers. But in level 2, primary and tangent part are dual numbers, and we could continue this to the higher numbers. But start with a simple interpreter for simple Fourier scheme subset. We demonstrate some evaluation of the interpreter on some simple function. For example, here we have evaluation of top environment, which is a standard environment for primitive function. And here we have a function on two arguments, x and y, and calculates a sine of x plus 3y. And it returns a closure with a variable, bound variable x and y. This is the body, and the remaining part is the environment. But forward application, forward evaluation of this expression also gives us the same closure. But how it helps us to calculate the derivative? For example, we could calculate forward gradient of a function that takes a list of real numbers and produce the real numbers on a list of argument of real numbers and produce a list of argument of real numbers. And this definition, this function define forward gradient of function f on argument xs, and you can see that it's a inefficient gradient using forward AD requires k round for function f from Rk to R. But this definition is in the host language. We like to be able to do this inside the target language. For example, this is an example of calculating 3a plus 5b at 17 and 19 should be 3 and 5, and can see in this implementation that the forward gradient of this function at this point is 3 and 5. Here, U1 on the EV top 3 and 0 is just real number 3, but at level 1, at level 0 is just real number, but at level 1, it gives us a dual number with the tangent part equal to 0. But here, you can see that in the level 2, if we evaluate this function, which is x times sine of x plus 1 over cosine of x minus 0.2 at 0.3, at level 0, it gives us the value of this function. But at level 1, it gives us the value of this function at level value of these real numbers at level 1, which is a dual number with 0 part as a tangent part. But if we apply this function on the dual number 0.3 plus 1 epsilon, it gives us the dual numbers, which the primal part is the value of the function, and the tangent part is the value of the derivative of the function at the point 0.3. But as a take-home message, we can add AD to a language by doing AD on the interpreter and tweaking, and can get higher order AD by nesting unified level 0 and 1 and generalize these to arbitrary level n. And first class AD is nestable operator of great fractional utility, and it's also making them super efficient. It's also for great fractional practical utility. And this presentation focused entirely on forward AD, but we could use the same idea for reverse mode by manually AD transform interpreter and unify level 0 or 1 and generalize it to level n and allowing nesting. Thank you for your attention.
Thank you, Mehrdad.
Thank you, Mehrdad. I turned off your video during the end of the talk because your bandwidth seemed to go down. So if you want to turn your video back on.
Yeah.
So do we have any questions?
Sorry.
I'll ask a question while we see if anybody else has got one. What have you used for implementation technology while you have done this work? What have you built it in?
Sorry. Can you please repeat the question?
Yeah, it's a. Here, I'll put it up as a question. What have you used for implementation technology?
MZ scheme. Yeah, MZ scheme.
MZ scheme. Okay. Do we have any other questions? All right then. Shall we take a? We still have 5 minutes to go before the next talk.
That's right. So we can get ready for the next speaker. So thank you again, Merdad, and let's go ahead and bring up Marc-Andre.